Okay, so we are deriving the expression for current in the presence of a contact here, which is non-ideal, right? Which is characterized by surface recombination velocity here. If we note here, this is a P plus N junction, right? So the current will be carried predominantly by, what will current be equal to? Right? So current is in general in a PN junction. How do we derive? What is it a sum of? It's a sum of two components. One component is whole current at this edge plus the electron current at this edge, right? So electron current at this edge is going to be, what is it dependent on? The electron current at this edge is dependent on minority carrier density in the P plus region, and minority carrier density is Ni square over Na. And if Na, P plus Na is going to very high, minority carrier density is becoming negligible, and so the electron current is negligible here. The whole current, of course, is going to be there. So the total current that flows through my PN junction is primarily the whole current in this region, correct? Whole current in this region. So that's the first part. The second part, the whole current in N region is it the whole current in N region? So it's a minority carrier current. Does it have a drift component or does it have a diffusion component? Which one is dominant? It has both. Which one is dominant? Diffusion component. Fine. So we can write this. So this is correct. I should have put an approximate sign. J equal to JP xn. Xn is this edge here. JP xn. Q dp, diffusion current. Delta P xn. Delta P xn is at this point. Minus delta P xn plus Wn here. Wn is the width of the neutral region here. Divided by Wn. Divided by Wn here. Is that expression okay? Diffusion current is what? Q dp, dp by dx. So what is the assumption that has been made here? dp by dx is the whole density is varying linearly, right? Linearly is varying linearly, and therefore, and why is it varying linearly? Because we are assuming that this is a narrow base diode. Wn is very small compared to diffusion length, right? So there's hardly any recombination in this particular region here, in the bulk here. And when there's little recombination in the bulk, we can easily show through continuity equation that one can the carriers then change linearly here. So that's why the linear variation that we've assumed here. dp by dx is simply carrier density here minus the carrier density here divided by Wn, right? So we can write this expression for whole current in this particular region here. Now, what do we do? Do we know this delta Pxn? Okay, delta. So we know delta Pxn. That's determined by Ni square over Nd exponent QVF by Kt, right? So we know the excess hole density here. So this part we know, but this is the part that we don't know, right? So this is where we bring in the property of the contact. The contact says that Sp, surface recombination velocity, is equal to Jp Q delta P at that particular point here, at the contact here. Delta P Xn plus Wn. Okay, so that's the property of the contact, right? So Sp is here. So what should I do? I can take this delta P Xn plus Wn here and write it in terms of Jp here and substitute it here, right? I will substitute it here. So this term becomes in terms of Jp. And then this is Jp here and this is Jp here, and simple rearrangement will give you that this is the expression. Q dp by Wn 1 plus dp by Wn into Sp delta Pxn by Wn. So it will give us this expression. So now we have an expression for current in a P plus N junction where the contact is not ideal. And non-ideality is being described in terms of the recombination velocity. So whatever is the recombination velocity, now that's a separate issue. How do I characterize recombination velocity? Okay, so these things can be measured and can be calculated as well. But we are assuming here that we know the value of Sp here. And once you know the value of Sp, then you can again calculate J. So now the issue is, I will never get a contact with SP equal to infinite. But do I really have to have SP infinite for a contact to be considered as ideal? When can you consider the contact to be ideal? Look at this expression. If I had SP equal to infinite, what would have happened? It would have happened Q dp by Wn delta Pxn by Wn, right? S goes to infinity means this term becomes negligible here. Now, it doesn't have to go to infinity. What does it have to become? SP has to be much, much larger than dp by Wn. That's it. All you care is that the value of SP should be at least, let's say, 10, 20, at least an order of magnitude higher than dp by Wn. And then you can consider your contact to be ideal. It's as good as ideal. Okay? So that's what you have to do. So we know dp, diffusion constants are known, Wn's are known. So you can calculate what this particular value is and then determine whether you can consider contact to be ideal or not. So if I give you a value of recombination velocity is 10 to the power 6 centimeter per second, right? Can I consider the contact to be ideal? It's very easy. You just see 10 to the power 6, compare it with dp by Wn and see if it's much larger than dp by Wn. Then for all practical purposes, as far as my calculation of diffusion current is concerned, it's ideal. The contact is ideal. Excess carrier density at this particular point will be negligible. Okay? So that's how you handle a contact which is sort of non-ideal here through the concept of surface recombination velocity. So it's a powerful concept used at many places wherever you have a surface or an interface, right? And we know that if you have excess hole and electron density, they will recombine. So in the bulk, we characterize recombination by lifetime. We have tau n and tau p and all that lifetime. At the surfaces and interfaces, we characterize recombination by recombination velocity. That's the concept that we use. So in the bulk, you have lifetime, and at the surfaces and interfaces, you have recombination velocity. And then what we showed here is how you use the concept of recombination velocity to derive an expression for current. Okay.